Welcome to another episode of Vision Basic. A percentage of Vision Basic users are relatively new to programming in general, so I've decided to focus more on videos that cater to the beginner, though I'm not going to take things all the way to the very start. There are plenty of resources out there for those who are completely new to programming in BASIC. BASIC is an easy language to learn and to program with, but a lot of beginners may struggle to piece together a program that does exactly what they are expecting it to do. Because you can learn all the commands and syntax, but these things are just the building blocks. It's like being given all the materials needed to build a house, but not knowing a single thing about putting one together. Sure, you could hammer some nails into some 2x4s, but your creation might not even pass the most basic of building codes. When you build a house, you start with the plan, or blueprint. So that's a great place to start when it comes to programming, planning out what you want your program to do. Sometimes you can keep all of that stuff in your head, but it's still a great practice to plan things out, especially for larger programs. Keeping a variable list on paper or in digital form is also a great practice. Sadly, you won't find me doing that in this video. But again, it's a great practice, especially for larger programs. Keeping an outline for the structure of your code is also a good practice, especially for larger programs. This outline might be a set of line numbers for the start of each section of code, including subroutines, followed by a description for each section or subroutine. The more you document, the better, especially for larger programs. And why are these all great ideas? Because it often bites you in the butt when you don't document things very well. How do I know? Because my butt gets bitten more often than I care to admit. Going back to our metaphor of house building, yes, you could read a manual on how to construct a house. But you can learn so much more by inspecting the houses being built by others. In the same way, a lot of beginners can read every manual out there on how to program in BASIC, but they'll be missing out on a very valuable resource, the examination of other people's code. Many of us quote-unquote veterans who started programming in the 70s, 80s, and perhaps even the 90s would study the programs of others, and we'd learn some cool tips along the way. Perhaps we'd even borrow a useful routine or two. And one of the best places to study the programs of others was in magazines like Compute Magazine, Compute's Gazette, Run, and Ahoy. And there are magazines in other countries that I never knew about. And these magazines often dished out programming tips in a reader's feedback section or dedicated columns or occasional articles that were centered around programming. PDF copies of these ancient relics can be found online with a simple Google search. So today we're going to take a look at a rather simple game program that appeared in the 1984 March issue of Compute Magazine called Rotor. As was typical at that time, ports were made for several different computers of that era, but the first program listing was for the Commodore 64. The goal of the game is to steer a car down a winding road and to avoid any obstacles that might be present. Over time, the road narrows and eventually becomes too narrow to navigate. If you hit an obstacle in the road, or if you hit the sides of the road, you're dead. Pretty tragic, right? Sounds like fun. Now, this video isn't going to focus on Vision Basic at all, but there are things you might learn that can be carried over into Vision Basic. The goal here is to teach basic programming, and in this specific case, we're going to analyze the code for this game and see what we can learn from it. But there are things about this game that bother me, and probably have bothered me from the very first time I've ever played it. For starters, the game is rather slow, and this is due to its reliance on the cosine function for making the road curvy. Another thing that bothers me is that the car is very blinky. So I'm going to show you a version of this program that I've modified that addresses both the speed of the game and the blinky nature of the car. I'm also going to show you a variation of this game concept that I whipped up myself from scratch that also attempts to address some of its shortcomings. And for my next video, I'd like to port it over into Vision Basic and see what else I can do to it. But first, let's take a look at the original game itself. We'll run it first and then go through the listing. One moment later. Okay, here we go. Get ready to watch me suck. Well, actually, it's not too hard on novice, however you want to say it. Here we go. Get ready. Oh my. I don't know, man. It's scary. I mean, look. I mean, I'm just barely staying on this road. Yeah. We could go for a while here, people. I mean, I know that the road is. Oops. Something on my screen just popped up. Excuse me. Gotta get rid of it. Well, there you go. I ran into this. I don't know if you guys can see what was on the screen, but yeah, I finally hit the road. See, you know what? Don't text and drive, and don't look at your computer screen and play a video game. You know, I mean, like, never mind, that doesn't make sense. Don't look at a pop-up while you're playing your video game. Yeah, there you go. Anyhow, let's try a different level. And we're going to go for Pro. Ooh, look, nice curves. Now this one's a little bit more tricky because you have to clear. Well, okay. Man, I suck even when it's slow. Okay, and then we have. Ooh, let's do expert because I'm an expert. There we go. I'm just poking a little fun at the game, but I mean, it's a cool little game. It's not very long. And just got to clear the houses. I think those are houses. I don't... Oops. Another stupid pop-up. Another stupid pop-up that came up on my screen and made it where I couldn't even control the car. How pathetic. Okay. And finally, let's try perfect, because, you know, that's me. I'm kidding. Okay, here we go. And yeah. Curve. I try to avoid the houses. Man, I swear. I am just ramming right into houses left and right. Okay, anyways. Okay, we're going to go ahead and exit. Press no. 5 to quit. And we're going to list through line 13. Now, I have spent a lot of time on this video prepping and everything, so I'm going to keep it simple. I'm not going to do a whole lot of pointing to things on the screen, so if I talk about a specific line, you just look for the line on the screen, pause the video if necessary, and we will work in that fashion. Thank you very much, and I need to turn the cursor white because invariably there will be a person who will, I guess their eyesight is not that good, so we are going to turn it... We are going to turn it white. Yes, there we go. And then list it again. Okay. Whew. Averted a disaster if I totally forgot that one, because I would hear about it in the comments. We all know that's going to happen. So, yeah. Okay. This is essentially the part of the program that sets up the menu screen. Line 0 forces the top of basic RAM down to location 12288 so that a redefined character set can be placed at that location. Honestly, I understand the lure of placing a character set and sprite shapes in the lowest bank of screen memory, but it also seriously restricts the size of your basic programs. And a lot of people like keeping the text screen at location 1024 because it's much easier to poke to that range of RAM from locations 1024 to 2023. But again, it limits what you can do to a degree. Even if your program can fit in the confined space, it might not fit the space if you run it through a compiler like Blitz, for example. There isn't a whole lot to learn from this section of code, but there are a couple of curious finds here. For one thing, I'm not sure why the C and M keys were chosen to steer the car with. I guess they're spaced far enough away from each other so that a person can use both hands to control the steering. When it's time to exit the game, I notice that it does so using an SYS 2048 at the end of line 9. This location, 2048, needs to contain a 0 for BASIC to function properly, so the end result is that an assembly language break instruction is executed with the SYS 2048, which is pretty much like hitting the stop and restore key combo. Line 2 calls a routine that redefines the character set. We'll take a look at that later. Now, we're going to list 14 through 42. Okay, line 14 clears the screen. If you don't recognize that character code already, you might need to go back and relearn some things, because that is a common character code, I promise. It clears the screen. Line 15 pokes a value of 255 into location 650, which allows key presses to repeat when you hold them down. Kind of like what happens when you press the spacebar and it keeps printing spaces to the screen. The default value for location 650 is 0, so this poke allows you to hold the C or M key down, and this allows the car to keep moving left or to keep moving right. See, if I press the letter A, I said A, it's only going to print it to the screen a single time, even if I hold it down. But this poke will allow the letter A to be printed to the screen repeatedly until I let go of the key. Since the program uses the get command to fetch key presses, it will keep fetching C or M repeatedly as long as those keys are being held down. And this was kind of a fun little poke that I also learned early on in my adventures of learning how to program. Okay, in line 17, the I variable is a step value for the cosine function you see in line 26. If a person selects levels 2 or 4, then the I value is doubled to 0.2, which will sharpen the cosine curve. Variable N is the starting screen position for the player's car in the game. In line 18, AM $ is set to equal 13 pieces of road characters. Now these haven't been redefined yet, so they look like a solid line. Now we have 3 nested loops in lines 22 to 25. We have an outer loop Q which repeats 4 times. I doubt the player will survive even one looping of Q, so I find this loop a bit unnecessary. In line 23, we have a loop that sets the road width, starting at the full 13 characters, and it counts down to a width of 0. And thus, that is why we don't need the Q loop. Because a 0 road width is going to guarantee that the car is going to crash into something. And line 25 contains the loop for the cosine input value, which is a radian value. I'm not going to explain trig functions in this video. These values are input into the cosine function, and a value is spit out that helps to create the curvy road. And this is where the algebra and trigonometry you may have learned in high school actually comes in handy. And in line 26, we create our cosine value. In line 27, we have a counter, the F variable, which I'll explain soon enough. Counters are great things. You can use them to delay the introduction of a player or an enemy, or other things, for example. The R&D value that goes into variable R controls how frequently an obstacle is randomly placed on or around the road. Again, I think they're houses. Reminds me of a song about a house being in the middle of the street. Can you name the song? I'm not going to explain the entire line here, but in 28 we are checking to see if the car is crashing into the characters that make up the edge of the road. Line 29 prints a single row of the road. The cosine value is multiplied by 10 and added to a value of 13. This value is used to tab out by a certain distance, helping to create the curve of the road. Just some FYI, but sine and cosine values weave between a range from -1 to 1, passing through 0. Anyhow, about half the time, the random value held by R is going to force a jump to line 40. This helps to limit the number of obstacles placed on the screen. Lines 30 and 32 work to plot an obstacle to the screen, but only when the counter F is greater than 25. Also, line 30 skips this process entirely if we're on levels 1 or 2. In line 40, the car character is poked to the screen, but only once the counter has reached 25 as well. A counter value of 25 allows the road to be fully drawn to the screen, which is 25 characters high, before the car and the obstacles are even drawn to the screen. The loop involving variable t here sets a small delay between the car being drawn to the screen and the car being erased from the screen. Despite the delay, the car flickers because of all the code surrounding this particular line. This is why using a sprite would have been a better choice. No flicker. We'll come back to that idea later. And line 42 seems to be a copy of line 28, which checks to see if the car has hit the edge of the road. In both lines, we branch to line 110 if the car has hit the edge of the road. Okay, list 43 through 80. Line 43 actually checks the joystick in port 2. This line really could have been simplified to put the peak inside the parentheses of the math expression for variable d. Lines 44 and 45 handle horizontal movement, but oddly enough, lines 46 and 47 allow the car to move diagonally, but only downward. So if the car moves towards the bottom of the screen, you can't reverse course. You're stuck there until you die. Line 49 fetches a key press. Line 50 is peculiar. This was the first time I had ever seen Boolean logic used to move a player. It's actually quite a shortcut. If the C key is pressed, a value of -1 is returned, causing the car to move left. If the M key is pressed, a value of -1 is also returned, but made positive by the negative sign you see here. So the car will move right. If there was one cool trick I learned from examining this program, it was this. And I have used it numerous times. Line 51 checks to see if the car has hit a house. It's curious that the object detection lines will trigger a crash if the car is even right next to an object. That doesn't quite strike me as fair. And line 80 finishes all of our nested loops, causing things to keep cycling back to lines 22 through 25. Okay. Lines 110 to 150 pretty much surround the car with explosion characters. Kaboom. Notice that when we jump to this line from within the nested loops, the loops don't get to be satisfactorily resolved, and thus removed from the stack. I find this an odd practice, and I'm guessing that BASIC will remove the old loops when they are reinstated as the program flows back through lines 22 through 25. But if you're a beginner, you will probably see it said this way, but you really should finish your loops. That's just overall good practice. Some languages are less forgiving than others in this regard. Lines 160 to 180 create an explosion sound for us. The poke in 190 kind of cleanses the keyboard buffer by telling BASIC that there are no keys in the buffer. Even if the keys are actually there, it says, hey, no, there's nothing there. Just ignore it. Lines 190 to 210 display the road width and a score, and asks you if you want to play again. The score is based off of the width of the road. Lines 215 to 240 fetch a response from the joystick or keyboard. Pressing Y plays the same game over. And pressing N brings us back to the menu. The pokes in lines 260 and 270 essentially expose the data for the uppercase character set so that it can be copied to location 12288. But here, we're only copying a fourth of the characters. We really don't need graphics characters, nor do we need reverse characters, so this helps to reduce the wait time for the player. The actual copying of character data is what is happening in line 280. Lines 290 and 300 restore locations 1 and 56634 to their regular values. Poking these registers is a bit dangerous. If there's an error in lines 260 to 300, the computer might crash. Ask me how I know. Line 310 sets the poke that allows our redefined character set to become visible, specifically at location 12288. And again, this is not a tutorial to explain how to redefine character sets or other complex things. We are just going through the program. You can copy what you see in the program for your own games if you don't want to dive into how these things actually work. Lines 330 to 365 contain data for the actual redefined characters, like the car, the road borders, the road itself, the house, and the explosion. This data actually redefines the first 5 graphics characters, so this program actually does use a few of them. And by redefining it means basically you're replacing them with your own graphics characters. Line 320 pokes this data to memory, starting at location 12800. And line 370 has us return, because this part of the code is a subroutine. Return to sender. Okay, so how can we make this game run a bit faster? And how can we eliminate some of the flicker going on? Let's load up a version of the program that I've already modified and take a look at the changes I made. I won't explain all of my changes in great detail, so examine the code and use a little bit of that gray matter in your head, but I'll do a decent job. Rotor with a plus. Okay, 260 onward. I tacked some code onto the very end that sets up an array to replace the sluggish cosine function that the game employs. The cosine function has a lot of repetitive values, so we can use this to our advantage. We only need to calculate 16 cosine values, and then we can figure out the rest by either duplicating them exactly or making them negative. In total, we'll need 64 cosine values, but since the game doesn't start with a radian angle of 0, I've extended this array to include 80 elements instead of 64. The value of 9.99 that you see in line 410 is there because we're baking in the multiplication of the cosine values by 10. But I used 9.99 because the curve pattern lacked perfect symmetry. If you change this value back to 10, you'll see what I'm talking about. Anyhow, calculating these 16 cosine values adds to the wait time at the beginning, but it makes the game much faster. I've also simplified the code in the lines above the ones I've added. I also eliminated some variables by reusing them, which should speed up the fetch time of those variables. And I'm defining variables in line 2 with a dim statement, which I don't know if I was really aware of this until more recently. Saw it being done in a 8-bit show and tell video. Generally, you want to have BASIC define the variables you use the most first. And let's see what else I've done. I've altered some line numbers and moved stuff around and deleted some things, so you'll need to put this code side by side with the original to witness the full scope of my changes. I eliminated the outer loop of Q because it just seemed completely unnecessary. The car is going to crash before that loop can cycle back. Notice in line 24 that we are defining the entire road segment before executing the inner loop in line 26. That way, by line 32, things are kept simple and quick. I've mentioned this in previous videos, but you want to reduce the number of calculations within an inner loop when possible, and this includes string manipulation. We've taken the left function out of the inner loop, so line 32 should execute faster. I'll Also in line 32, we skip a whole bunch of stuff if the f variable is less than 25. This allows the road to fill the screen a lot faster, though it might be a bit jarring to you when you first see this in action. I have combined some stuff together on line 35 to help simplify things. Notice the period within the parentheses for the R&D function. This is a trick that is supposed to execute faster than supplying a 0. And by the way, 0 is not the best parameter to use with the R&D function. You're not going to get perfectly random results, so you're probably going to get some spacing out of some values and whatnot. For example, if you try to fill up the entire screen with random stuff, you might see that it's not quite filling up the screen fully. In line 40, I'm simplifying the reading of the joystick port, as mentioned earlier. Originally, there were 2 expressions, but now there's just one. And in line 44, I've combined 4 lines of code that help to move the car based on joystick input. No more if-then statements, just some simple math to get the same job done. The only difference between what I've done and what you'll find in the original code is that the car can now move straight ahead and not just diagonally ahead. And in line 50, I've combined 3 collision detection statements. This might actually make the game a little less difficult, but I'm okay with that. We're detecting objects around the car, and the shape of the area being surveyed is triangular. Whether the car changes position or not, we're checking under the car, to the left of the car, to the right of the car, and to the front of the car. I've changed the technique that was used for detection by OR-ing all of the peaked bytes and then masking off some bits to see if any of them are the result of a character being a road border piece or an obstacle. And I'm even including the space characters to each side of the road, in case the car can somehow squeeze between 2 road border pieces. I don't think that's possible, but anyhow, we're checking. And it doesn't really cost us anything. And this all kind of works by chance, though. If you break down the character poke code values into the respective bit values, you'll see that the car is poke code 64. See line 31. And the value of 64 is a bit value all by itself. You just have to remember your powers of 2. 1, 2, 4, 8, 16, 32, 64, and 128. So we want to ignore the bit value of 64. The poke code for the road is 68, and that is comprised of bits with the values of 64 and 4. 64 plus 4 equals 68. So we need to ignore the bit value of 4 as well. So let me type it. 64 plus 4. We don't need to focus on either of those bits. The road border is poke code 65, which is bit value 64 plus 1. And the house obstacle is poke code 66, which is bit values 64 plus 2. So we can look out for bits 1 and 2. 1 and 2. And the space character is poke code 32, which is bit value 32 all by itself. So if we combine bit values 1, 2, and 32, we get a grand total of 35. And that's why you see the value of 35 in line 50. So again, we're masking off bits 1, 2, and 32 to see if the car is colliding with the road border, the house obstacle, or the space character. And again, we're simply merging all of the bits of 4 peak values by using the OR operator. And again, this all happens in line 50. And I simplified things further by checking to see if the car has not collided with anything, thus the 0 at the end of the statement. In this way, we can issue our 2 nexts to keep the loop going. If a crash occurs, we instantly fall through to the next line, which incidentally handles car crashes. Now, to reduce the flickering of the car, I use an old technique of mine where you try to erase the car in its previous position right before drawing it to the screen again. You really have to narrow the gap between when you erase the car and when you redraw it again. So I added 2 variables in line 15, V and W. When these values are first poked, they're off-screen locations, both pointing to location 2024. This is a generally safe location in most cases. Variable V is for the previous screen location, and variable W is for the previous color location. Since no previous location yet exists at the start of the game, I simply set them to location 2024, even for the color location because it doesn't really matter at this point. Location 2024 will get poked to twice. No harm, no foul. So in line 31, you can see that we are poking the previous location and then poking to the new location. We only have a print statement between them, and this is necessary. I wish I didn't have to have this print here, because it does force a bit of flicker. We must erase the car right before scrolling the screen up by a single line. Otherwise, you'll see the car scroll up with the screen for a brief moment, and we don't want that. Anyhow, print is the only command that needs to be here. Sadly, scrolling the screen up does take a lot of cycles, but the flickering is certainly reduced from how it looks in the original game. At the end of the line, you can see that we copy the current screen and color locations into variables V and W. I do want to point out one problem with this game, both with the original version and the version you see here. If the car drives past the bottom of the screen, there's nothing to stop it from overwriting the program code. I tested this out with the original program driving past the bottom of the screen, and when I halted the program execution with stop and restore and listed the code, I could see the letter D appearing in random spots within the code. We could put something in place to prevent this from happening, but the purpose of this modified version is to show you how to speed up the original program. Anyhow, such an addition might look like this. 46. If n is greater than 183, then n equals n minus 40. I've tested this and it does work, in this program specifically. You want to prevent the car from hanging out on the very last line of the screen because when the car does crash, the explosion could end up extending into the program code as well. Anyhow, my code alterations to this program have reduced the main game loop by 8 lines of code, though I did add lines 400, 410, and 420 to the very end of the program. So let's see the results, shall we? And by the way, as far as flicker goes, because of the capture rate of the video capture, the flickering, I don't know what it's going to look like, but it has been reduced. And let me type run. And we'll go novice. Okay. Pretty sure you can tell the difference if your memory serves you correctly. Yeah, I wanted to point out something as I'm driving here, but there's a gap right about here. And well, actually, the car also, this version also detects spaces, so it would crash anyways, but I'm pretty sure in the original game that if you try to drive through that, it'll still probably crash. But it would be kind of fun if you can just kind of drive on the grass or dirt or whatever that is on both sides. I'm not entirely sure where this is at. This could be some weird, crazy neighborhood where the roads just go left and right and whatever, Anyhow, so faster, yay! And the car doesn't blink so badly. And again, since you're watching a video capture at 30 frames per second, half of the C64's 60 frames per second won't be visible to you. And now let's take a look at a variation of this game concept that I wrote completely from scratch. My goal here was to make a faster variation than the original game, and I wanted to completely eliminate the blinking of the car. The basic gameplay remains the same. I created this program before I created my modified version of the original Rotor game, so this program isn't necessarily as fine-tuned as the previous program. I chose multicolor character mode for my game, though one of the main reasons for this choice won't become apparent until my next video. Still, multicolored characters are a bit more fun to use. I call my game Potholes, so as you might be able to surmise, the goal of the game is to avoid the potholes instead of houses. Let's go ahead and see the game in action, shall we? And first we got to get out. And press 5. New. Layered potholes. With exclamation. And I have a cat meowing outside the door. Just ignore her. And here we go. One moment, please. And we're going to select, let's just go with one. And the keys I need to use for this game, I chose the period and the comma, which is where the less than and greater than symbols are. So in my mind, it made sense. Okay. And this is my version of the game. And we are driving down the road. Oops. Kaboom. Okay, so as you can see, since I named the game Potholes, I can't exactly have any levels without them. You might also have noticed that the car is larger in my game. Well, the road kind of dwarfs the car in the rotor game, so I think the game calls for a bigger ride. You might also notice that the road is moving the opposite direction. In other words, we're driving up the screen. There's no machine language being used here. It's a simple trick to pull off this effect, but I certainly can't take credit for it. Notice that we're also able to display the score at the top of the screen while the screen is scrolling. And I'll show you again for, if you didn't notice. To help speed things up, my game actually doesn't employ the cosine function to give our road its curvy shape. And I'll play one more time. And let's see. I think it's enter. Yeah, return. Sorry. And we'll go with 3. Yeah, just notice a few things while you're playing the game. You'll notice the score at the top of the screen. You'll notice that the screen is scrolling the other way. It is the screen itself is not scrolling up. It's scrolling down, but the car is driving up, if that makes sense. Okay. So just pay attention to some of the differences here to my game versus the original rotor game. Okay, now gotta get between the potholes. This is okay. Well, that was one issue. I do use sprite collision detection, and it's kind of sensitive. So yeah, we barely nicked that pothole, and yeah. But the original rotor game was pretty much like that anyway. So yeah, very sensitive. You could just barely touch it, barely touch it, and kaboom! Your warranty is voided or something. I don't know. Anyways, we are going to exit. Let's look at the code, shall we? Now, I tried my best to make my code easier to read than the original rotor code. I tried to put comments and different things in there, rim statements and whatnot, and just try to organize it a little bit better. I think that it's almost like the original rotor game was kind of just written in a really hasty manner. No criticism to the original author, but that's just my impression. Okay. In line 0, we're again going to lower the top of basic RAM so that we can have a redefined character set at location 12288. Fortunately, this game isn't huge, so it won't run out of memory. In line 10, I have defined some variables early on. Again, since these variables are defined first, BASIC will be able to access them faster, and thus the commands that use them will execute a little faster as well. Plus, they are actually used to replace values within the program, because BASIC is a bit slow at parsing actual numbers, especially ones consisting of more than a couple of digits. Line 20 tells the user to wait a moment. Line 30 calls the routine that redefines the character set, which starts at line 8000. As you examine this program with me, notice that a lot of the sections of code are spaced apart by thousands. This gives me plenty of space for my code to grow as needed. Line 100 calls the title and menu screen subroutine. We'll take a look at that when we get to it. Lines 110 and 120 set the screen colors and multicolor character colors. And line 130 turns on multicolor character mode. And line 140 makes the redefined character set visible. I'm here to help you focus on program structure and pass along some tips, but I'm not going to explain the pokes to any depth here. Line 150 sets string variable R $sign to equal a row of road characters. The $sign character in the road string is used for the road border, and the and symbol makes up a row of our road. These are two characters that are getting redefined. I don't have a $sign at the end of the string because we're only going to print a portion of the string based on the width of the road. And then we'll print the dollar symbol after. These are two of the characters that get redefined, since we won't really need to display a $sign and an and symbol during actual gameplay. In line 160, we have a lot to explain. Creating this string ahead of time will allow us to print all of these characters faster, since BASIC won't have to parse all of the functions and such during gameplay. We want whatever speed we can get, folks. But this is also where some magic happens. See, the secret to scrolling the screen downward has everything to do with this one string. When string $sign is printed to the screen, we first home the cursor, and then move down to the next line. And then we cursor back to the end of the first line. So I'm going to illustrate this with my little pointer here. This string here forces us to home, then we go down, and then we back up to here. At the end of the top row of characters, we then issue an insert. This is what the character code 148 is for. And this pretty much causes BASIC to push the screen down and open up a new line on the second row of characters. So again, up here, right at this very exact spot, we are issuing an insert. When the insert happens, a new line will open up here, forcing all of this down by a row. And there's the magic. The rest of the characters in the string set things up for printing the next row of road characters. Since the top line doesn't get pushed down, and I'm pretty sure you can't push it down anyhow, it makes a great place to print the score and any other information you wish to display for the user. The return character code 13, helps us to escape insert mode, which causes control codes to be printed as reverse characters instead of actually doing anything useful. Now again, I wish I could take credit for this neat little trick, but alas, I cannot. I saw it being used in a 10-line VIC-20 basic game called Avoid, and I wondered if the trick could be carried over to the Commodore 64. And sure enough, the trick also works on the Commodore 64. When I first encountered this VIC-20 game, I thought some kind of machine language was being used to scroll the screen downward. So I pored over the code and I simply couldn't find any. I thought that perhaps there was just some special mode that this VIC-20 had that the C64 didn't. Eventually I figured it out. It was so simple, and yet I had never run across this trick in all of my years of programming the Commodore 64. It's important to mention that a special poke is also required to make all of this work. See, you can cause the insert to happen, which opens up a new line and pushes the screen down by one row of characters, but if you try to do it again, well, the computer now sees the top two lines as a single logical line of 80 characters, so the trick stops working. So you have to poke one of the registers of the line length table that spans from locations 217 to 242. The one register we need to zero in on, though, is register 218. Now, this is not exactly an area you want to toy around with if you're a beginner, so just warning you. You'll see this poke in action soon enough. Anyhow, the poke forces BASIC to see the second row of characters as no longer an extension of the first row of characters. Going back to the Avoid game, I noticed that the spaceship flickered a lot during gameplay, so I wanted to see if I could minimize it. The flickering. I know almost nothing about the VIC-20, so it took me a bit to figure things out, but I managed to reduce the flickering significantly, and I was able to keep the game confined to 10 lines of code, just like the original game. I also learned that I don't ever want to use the editor on that machine ever again. No. Program listings zoom upwards way too fast for my liking, and I find it hard to read the code listings in general. I don't mean any offense to those who love the VIC-20 though. I have seen some pretty impressive games and such made for that machine. Moving on, line 500 defines some variables for our game. The F variable is used as a counter to allow the road to be fully drawn to the screen at the start of the game before we bring the car into the picture, just as it was with the previous game. Variable E is used to help space out the potholes a bit, because there was a tendency for the potholes to cluster together and prevent the car from being able to pass. Variable X is the X position of our car sprite. Variable B is used to calculate the curve of the road. SC is for the score, which pretty much just increments by 10 for each row of the street that gets printed to the screen. V and W are used to modify the road curve a bit, and using variables here instead of values helps to speed up the program execution. Variable U is also used to improve program speed, and it's used to indicate which line the potholes are poked to the screen. 1300. And here is our gameplay loop. In line 1000, we clear the screen and we print the word score at the top. And for the sake of speed, we don't want to print this word over and over again because that's just extra drag on our program. So it's outside of the main game loop. Line 1010 is the loop that sets the width of our road, which becomes more narrow over time. Line 1020 simply shortens the road string to match the width set by variable C. Again, placing this outside of the main loop helps to speed things up. We don't want to keep using the left function over and over with each pass of the inner loop. I gotta change the cursor to white. I'm not gonna redo anything here, people, but okay. I don't want anybody complaining. I know that part of the program, heck, I don't even know how far back it goes. I'm going to hear it, I know I will. There will be that one person who feels so proud that they were the first to mention it. They're going to cry tears of joy. I mentioned it. I complained about the colors. Okay, continuing on. Line 1030 holds the loop that helps us create a zigzag pattern for a road. Line 1040 makes sure that variable A gets converted into a positive value, which ensures that the zigzag actually happens. Without going into too much depth here, we kind of average the value of A into the existing value of B, giving the original value of B 15 times more weight than the value of A. This helps to soften the pointy ends of the zigzag, in effect helping us to avoid having to use the rather slow cosine trig function. The resulting curve isn't a perfect match to the cosine function, but I'm satisfied with the results because I value speed here over accuracy. The calculation for variable S at the end of line 1040 is just some fine-tuning I use to get the curve to fit the screen space better, so that the left and right curves almost hit up against the edges of the visible screen. In line 1050, we print the score and one row of characters that make up our winding road. There's no need to use two print statements here. And line 1070 uses our special poke that allows us to repeatedly insert new lines at the top of the screen. Variable CR checks the sprite to background collision register to see if the car has hit anything. And line 1080 will close the inner loop and prevent player interaction until the road fully fills up the screen. The collision register gets needlessly checked a bunch of times, but this actually helps to ensure that it's cleared before we actually inspect the value. The register is cleared whenever it is read, and if you don't clear it out ahead of first use, you might end up with a false reading. And this is a common mistake made by beginners, not clearing that register out. Line 1100 pokes the appropriate registers to set our car sprite's horizontal position. The vertical position never changes, so that helps with the speed. And since we're only using one sprite, poking that extra significant position bit can be done quick and dirty with a simple x divided by 256. Line 1120 checks the keyboard for the comma and period keys. I'm using this technique of peeking location 197 because you don't end up with any lag like you do from using the get command. The values from location 197 don't really match true ASCII code character numbers. So you'll need to test the values returned yourself with a simple line of code in direct mode. Here we have the sprite jump 8 pixels at a time, left or right, because we're not going to get satisfactorily smooth results in regular BASIC. The screen moves 8 pixels at a time, so our car also needs to move 8 pixels at a time. Line 1200 is our little counter that helps to space out our potholes a little. Line 1210 generates a random number and compares it against the chosen level number to help decide how often to add a pothole to the top row of road characters. Line 1220 pokes the pothole to the screen and resets the spacer variable E. And line 1300 will complete both game loops as long as the car hasn't crashed into anything. This whole section of code that you see right here is all that's needed for the gameplay. The simplicity here helps speed things up. This section doesn't need a lot of explanation. I decided to go with a simple explosion sound, and a handful of simple pokes make that happen. Line 2030 prints a game over message and tells the player to press return to continue. Line 2040 changes the car colors a bit so that we can have our fiery explosion. Lines 2100 and 2110 generate a couple of random numbers that pick a random location within the sprite shape and store a random value to that location. This creates the fiery explosion effect I was looking for, though it runs a bit slow in regular BASIC. I still think the effect came out decent. I use an array variable m to mask off parts of the sprite that I don't want to affect. My mask is pretty much a sprite shape in the form of a solid but elongated circle, matching the dimensions of the car shape itself. The AND operator here performs the masking. And line 2120 waits for the return key to be pressed, and line 2130 sends control almost back to the start of the program. We want to bypass the part that copies the character set and redefines some characters, but we do need to restore the car shape after being mucked up by the explosion effect. I thought I would need more subroutines in this program than what I ended up with, so I have no routines in the 3000s, 4000s, 5000s, and 6000s. We just pretty much jump to 7000. Line 7000 defines variables XL, XH, and CO, which are used in the game loop in place of actual values. Again, this helps to speed up program execution. XL and XH are used here in line 710 to clear the sprite positioning registers. Variable CO is for collision detection. In line 7020, we are setting the car sprite to a location off-screen into the right border area. We don't want our car to touch any kind of solid characters, thus triggering a collision before the game even starts. And since the car's initial starting position has the most significant bit set, we're choosing the right side of the screen now so that we can keep the most significant bit set, because I suppose it's possible for the car to land on character data on the left side of the screen before the car's most significant bit can be set. And that was a mouthful. One might think that it's possible that a collision could be triggered anytime the sprite's position jumps from a horizontal position of 255 to 256 or from 256 to 255, as there is a brief moment between setting the lower 8 bits of the X position and the 9th most significant bit of the X position. But I haven't experienced any kind of unwarranted collision detections yet. I think the lower 8 bits of the X position jump from a value of 248 to a value of 0, and from 0 to a value of 248 when that imaginary line is crossed between the 28th and 29th character columns. And so if you combine a value of 0 with the most significant bit of 0, you're off screen to the left, and if you combine a value of 248 with the most significant bit of 1, you're off screen to the right. So the crisis is averted, methinks. Now that's a lot to dish out there, but the point is that in some cases, if you're trying to use collision detection and let's just put, if the sprite is crossing from, say, this side to this side, you have, it's not on screen right now, but you have this situation where the distance between setting the first 8 bits and that 9th bit, there's that little pause there. If the screen tries to draw the sprite in between the pokes, the sprite could end up in the wrong position visually and end up triggering collision detection. I think that's just the best way I could put it. And I'm just assuming that this can happen. Collision detection is really kind of tricky on the Commodore 64, and it's not something I really care much for, at least not using the hardware version anyhow. So, let's continue. Okay, so lines 7030 to 7070 clear out some sprite attributes, making sure that our car doesn't appear expanded vertically or horizontally by accident, for example. And we're also setting the Y position and the 3 colors for our car. We're also turning the sprite on and setting its shape. In line 7090, you can see that our sprite shape 11, is pulled from our data statements and fed into the safe area from location 704 to 766. As you should know, there aren't many safe places in lower RAM to store sprite shapes. Now, I suppose if you're going to put a character set in that lower RAM and you're not going to use the entire character set, you could probably use some of the area of what would be the character set to store sprite shapes in. And that's just, some little advice there for anybody who needs more shapes than just, say, 4. Because the area before the screen is there's maybe 4 shapes total that you have access to, and that's it. And we're using the restore command in line 7080 because we need to restore the car shape each time it gets decimated by the explosion effect I showed you in lines 2100 and 2110. Okay, there's not a whole lot to explain here except that I'm restoring the screen to have the regular character set available and turning off multicolor mode in line 7104 by poking the default values to locations 53272 and 53270. In line 7220, we are setting the chosen level, which goes into variable L. The screen gets cleared and then we return back to line 100, which is where this routine gets called. Lines 8000 to 8050 are similar to some lines in the rotor game, but I'm using some math to create an offset value, which will help to reduce how much math we're using within the loop. In line 8030, which copies a portion of the character set. You'll notice that we only have a single expression within the loop instead of 2. We're poking I plus OS, but we're only peeking I. It's one math problem instead of 2, so it executes faster. It's also important to notice that I'm copying only 1/4 of the character set, like with the rotor game, for the sake of speed, but also that I'm copying reverse character patterns over to what is supposed to be non-reverse character patterns in the redefined character set. I'm doing this because I need the space character to be solid. See, the screen is normally filled with space characters when you clear the screen, and I want to take advantage of that freebie of sorts. Since we don't want the car to wander over into the grassy areas, having them comprised of reversed space characters is a simple solution. Otherwise, we'd have to fill the entire space ourselves with some kind of solid characters, and that would take more computer cycles to print. We'll just make the character for the road a blank square with no pixel data within it, thus suppressing collision detection on the road itself. And line 8060 skips past the sprite shape data for our car, since the routine at line 7000 already reads this data and pokes it to memory. We do this so we could get to the mask data, which is read into the M array in line 8070. Line 8080 has a poke that I've rimmed out. I just put it in there so I could watch my redefined character shapes as they're being poked to memory. The next section of lines read the character data that I have set up for redefining a few characters, but I chose an unconventional approach as opposed to using simple poke values. Anyhow, I'm not going to explain the intricacies of this code. You can see that I tried timing how long it would take to read and poke the character information, and I got things down to about 1 second for each redefined character. This routine takes a Vision Basic approach to character redefinition, and you'll see what I mean here in a minute. But before we get to the character data, as you can see here, I have my sprite shape data used for the car, and also the masking data for the car explosion effect. Okay, so here you can see that I'm using a binary approach for my character data. In reality, these are just decimal numbers that my subroutine interprets as binary values. So in line 9500, that number is really 100,000. And they're not read in as strings either. My subroutine just breaks each number down by digit and produces pokeable values from that. It didn't occur to me, though, that the images you see here are flipped from what they will look like in their final form as characters. I suppose I could try to fix that, but the resulting routine would likely be slower, in my opinion. As it is, my characters are multicolor in nature, so you have to group the digits off into pairs to be able to assess which multicolor values are being referenced. And the road character is embarrassingly simple, all zeros. Anyhow, the reason I took this approach is so that I could easily go in and edit these characters by tweaking the values, and using binary provides a visual on what the characters are going to look like. But since it does take 3 seconds to interpret all of this data, I decided to create a separate version of this program where the bit pairs have been converted over to values from 0 to 3. This sped up the process significantly, so let's load up that version. Sorry. And here is the improved version of the character redefinition routine, and I noted here that it only takes 1.83 seconds to define the 3 characters now. You won't want to use this approach to redefine a large number of characters, though. And here is the data. Now, the images are still flipped, but again, I can live with that. Here you can see that we're using colors 1 and 2, but don't confuse that with the actual colors of white and red. In this case, 2 is black, because we set color 2 to black. We don't need to list the third character shape, because it's just going to be all zeros again. And I could run this version of the program, but the only difference you'll notice is that the prep time is less. But I did create a third version of the game, which is meant to mimic the road borders you see in games like Pole Position. So I'm going to load that version instead. Potholes plus. That's 9497 through. No. And in the first character matrix, you can see that we've added a third color, color 3. Now, normally this would appear green because it's the main character color, so I had to manually flip the green color over to red and then back to green when we're done printing a row of road characters to the screen. This works quite well, but there is a downside to doing this. For example, if we want to do a smooth scroll with the help of machine language, there aren't enough cycles that I'm aware of to shift both the screen and color RAM by a full character width. Okay, so let's run this version so you can see the new theme in action. Okay. And there you go. I mean, not precisely pole position. I'm assuming that the areas of red and white are probably a little longer than that, but the basic idea is just to, make it look similar. That's it. And hey, why don't we do 6? Let's see what happens with 6. Level 6. How hard is 6? Yeah. Okay. Whoa. Oh well. I assure you, I'm a much better driver in real life. But I do hit potholes from time to time. Now let me get back to, let's crash here for a second. Okay. Now, one downside to this redesign is that the car can collide with the red pixels. So this, in effect, actually narrows the road a little bit. When the car collides with the white pixels, collision detection doesn't respond, actually. Apparently, the first multicolor character color is treated like the background color. The register for color 1 is 53282, in case you were wondering, and need to keep this bit of info in mind. One other note I'd like to throw out there is that the C64 allows you to have both high-res characters and multicolor characters on the screen at the same time. You might know this, but you might not. In order for a character to appear in multicolor, you have to use a character color in the range from 8 to 15. And even though these colors typically appear as lighter shades of the other 8 colors, they'll appear as the regular color shades in multicolor mode. So a character of light green will appear as normal green in multicolor mode. And this only applies to the actual character color that you poke to the color RAM at 55296. Colors 2 and 3 can be any shade from the available 16 colors. In my next video, I'd like to bring this program over into Vision Basic and see what I can do with it. But I did compile both the original Rotor game and my Potholes game with the Blitz compiler to see how much faster they'd run. I was concerned that dropping the top of basic RAM down to 12288 would cause an out-of-memory error, but fortunately, the compiled programs still fit the smaller space. Now, Blitz can improve a lot of basic game programs, but I was often left frustrated with the results because I needed even more speed in most cases, and so that's why I created Vision Basic in the first place. Anyhow, let's see what Blitz can do for the original Rotor game. Okay, play it a little bit. That was fast. And we still have the blinkiness, but the road is printed faster. At least a little bit. Okay. Now, one issue with the Rotor game is that the cosine function still slows things down significantly, even after being compiled with Blitz. And the explosion effect at the end executes a bit too fast. Okay, so I also compiled the version of the game that I optimized, and we will see how that goes. Ooh. And we'll run it. And we'll play it. Now this is this actually makes it challenging. But remember, this is my optimized version, compiled with Blitz. Okay, and if you play the other levels, let's just try 4 for perfect. You'll see it's practically impossible to play. Let's try it again. I mean, it's just too fast. And now let's load the compiled version of my game. Press no, 5, and new. Potholes ++. And we'll play it. Okay. Get ready, set, go. And as you can see, the explosion sound remains unaffected, which is good. But the explosion itself, the visual aspect, looks significantly better in my opinion. Looks so much more fiery. After improving the original Rotor game, I decided to go back and see if I could apply techniques that I used on the Rotor game to my own program. So here's the improved version of my game, compiled with Blitz. And exit. X, new, load, potholes, and 1. And let's try it again. It was terrible. Terrible, I tell you. Okay, a little bit bit difficult on that first level. Now, when I port the game over into Vision Basic, I have some ideas on how to improve the actual gameplay, because it's a bit difficult, as you can see, to play the game for any appreciable amount of time. It might also help to let the player know which keys they're supposed to use to play my game. I kind of forgot to put that in my game. My apologies. Again, it's the left and right, or greater than left than symbols, but actually you're just pressing comma and period, and then of course you press return as whenever you crash. So, yeah, kind of simple, but people will possibly be flying a little bit blind if they don't know that, so my apologies, but I don't have time to go back and make all the changes. So anyhow, I was going to add some news bits to the end of this video, but it's taken longer than anticipated to put this video together. I mean, a lot of work. So I'll wait until next time. To update everyone on my progress with Vision Basic 1.2, I recently overcame a major hurdle before I started this video. I pushed the pause button on my work with version 1.2 when I started work on my last video, which was a news video. And when I came back to resume working on version 1.2, I realized that I didn't document my work very well. So I came back a bit confused at what the heck I was looking at when I started re-examining my code. The code I've been working on is very complicated, so leaving it in an unfinished state was a bad call on my part. Anyhow, again, I overcame a major hurdle, and I only have a couple of smaller hurdles left to overcome. I'm not saying that they'll be easy, but anything's got to be easier than what I just went through with the last hurdle. I'll see if I can overcome those hurdles between now and my next video. And alright, we have reached the end of this video. As usual, I thank you all for watching. Please like and share my video, and definitely subscribe for more similar content. And make sure to visit visionbasic.net.